Hello, I'm Giulio Alessandrini. I talk today about computer vision in Mathematica, and I will talk tomorrow about image and signal processing and sound processing in Mathematica. I started working with Wolfram 1 year ago. I come from physics, and I'm actually in the image and signal processing team.
So we will try to, I will try to outline a bit what you can do in the upcoming Mathematica 10 in the computer vision area, mainly with a like small easy application example through which I can demo a couple of new functions that we have. That some of them really powerful, and we're expanding, we're working on a lot. So we just to get soft start, we start with some new functionalities, new low-level functions that, building block that you can use for to build your algorithms, and then we'll have three applications examples. So first thing, we have added barcode support to Mathematica. So if you want to use Mathematica also in conjunction with those things like Raspberry Pi or external device project, you can use it as barcode reader and barcode generator. So we can create barcodes in, this is the hyperlink for, you have to initialize, the hyperlink for this conference website. And you can generate, first time it has to load the library, but usually it's faster. You can generate like 2D and 3D barcodes. In this case, they are like 2Ds because it's string. And we support, for example, QR code supports error correction, so we support that as well. And of course, since we have barcode generation, we also wanted barcode recognition. Barcode recognition, for example, in this case, is just generating a string, converting, and getting it back. You can do with, okay, this is just a pure barcode, really perfect, just generated, but this works with all kinds of barcodes. This is an image that I took yesterday of a book I had just close by. So it just recognizes, this is an ISBN code of a book, and then I use, oh, no, I don't have internet, sorry. You can use ISBN to look up for, let me see if I can make this work. Probably I have to restart this hotel connection. Let's leave it for now. It's not so important. You can do a query on the web for the ISBN and get back. I was getting back the page from Amazon where you can order the book or something like that. And with this new connected device project, you can also build your. This is like a really small example that shows how with a few lines of code you can build your own barcode reader. So you'll just open the device. It's finding and opening all together. Yeah, this is my camera. And I just set the frame rate to 2 because I don't want to call too much barcode recognize real time here. And I think of course, I forgot in my hotel my example of barcode, and I don't have one. But this thing, does any of you has barcode? Okay, I'll take my time with trying to make this work. So let's try. Okay, hello, it's me. Let's try this. Oh, it works. Great. So this is an example of the bounding box. I don't know if you can see it. It disappeared now. Okay. So this is brain food news, whatever. I'm moving too much. Okay, thank you. And so, yeah, this is a small example of what you can do. Let me close this. It's memory intensive. And then we will just close the device. So a few lines of code, you have your barcode reader. Of course, you can do everything you want with this camera. Okay, another application, another function. We have implemented GrowCut segmentation in Mathematica 10. What is GrowCut segmentation, if you're not familiar, is segmenting algorithm which is basically based on cellular automata. It will grow the automata based on some seeds that you place. So for example, here I have an image. I prepared, it's not my cat. I've prepared foreground and background mask with an image mask tool. And then this is basically what this thing is doing in the pseudocode. So for each iteration, you take the pixel. Pixel is represented by a label. Label message will be the final segmentation, a strength of a pixel, and a feature. For an RGB image, usually the feature is an RGB triplets, and the strength you can initialize everywhere it to 0 and 1 when you put the seeds. So the seeds are strong, and they will try to fight to get the region in the image. And then at every step, the seeds, the pixel will basically will have a fight with the other pixel, and if the strength weighted with a feature function, you can usually, this is a decreasing function of the color, usually it's bounded between 0 and 1. So it will basically, it's a weight that will control how do you scale the strength. You do that with the intensity of a pixel usually. And if the fight is won by the attacking pixel, the label will be expanded on that region. So this may sound a bit obscure. Actually, it's really simple. So let me see. These are the strokes that I draw on the image. This is iteration 1. So let's go ahead. And you see this is growing. And when they are touching, basically, since there's a boundary there, this thing is taking the shape of the boundary. And in the end, you have the final segmentation. So this is growing using the markers till it reaches, hopefully, the boundary of the image. So of course, it is boundary dependent, but you can have really, really neat segmentations in the end. So this is what you have. And you see that you can get, let me do this a bit bigger. You get the two areas. Also, we have like a pretty good result on the this like the hair of the cat. That is usually a bit difficult to get with other methods. Another function that may be useful, both for like analyzing image or kind of image microscopy, or in this case I'm using on text, is local adaptive binarize. What is local adaptive binarize? Basically, we have binarize function and morphological binarize, but they all work. I mean, they need like constant level of background illumination. What in a case like this? Here you have a gradient. So if I apply binarize on this, it will get a dark area and a light area, and this won't work. So with this is a super big image because our text synchronized need to be improved a bit. You maybe have noticed. So I'm importing the result of local adaptive binarize here, and you see this is just this function call. It takes some time, so I won't call it now. But this is binarizing the images using a neighborhood specification. And so you do this, and if you do text recognize, here I had the result. Text recognize on the original image was the letter K. Don't ask me why. If we use this binarized image, we just with no other pre-processing, so we're a bit crude, but still, we get most of the text correctly. I mean, some of them, the items of the punctuation things are not perfect, but still, you get a lot of correct text already with no pre-processing whatsoever, apart from local adaptive binarize. So that says that these three functions, I choose them here because they are, I think, nice and really useful as building blocks. Let's go a bit ahead. This is another new function. This is we are introducing in Mathematica 10, which is image saliency filter. Right now, we implement the ET algorithm for salience. This is basically a combination of 3 different kind of maps. So we measure saliency of image using the intensity of the image, using the color contrast in the image is based on color opponency, and we use the orientation of the image. This is based on Gabor filters. So this thing works by building a lot of maps, normalizing them in their intensity, and then comparing to put together the salient region. And you see, for example, here, you have intensity map, color map. I don't know why it's dark. What am I doing here? Oh, yes, because this, what is this? IMG. Oh, because this is the black and white image of Marcus. Let me go back again. I took this image, this just clip art from the internet, so this should be like, of course we expect this red region to be the most salient one is supposed to be. And have I evaluated again? Yes, okay. So now you see in the light region are the high contrast region when you change from color to background are highlighted in the intensity map. In the color map red is popping out really clearly. And the orientation map, you can call it separately because you may want to use just one of them. Maybe you don't need all of them for your applications. You have basically, is using Gabor filtering to get in the orientation, the strength of orientation in the central, of a feature in different orientation. And the combined map is weighted in order to get like the correct mixing of the three. So once you get this with the final map, you can easily trim, for example, the image, and you get the most salient region. Hopefully, we hope to get the most salient region of the image. And using this, I built for the talk just like simplified version of a gaze tracker. It will just track where the eyes are moving on the image. This is an image with many salient regions, so we are not supposed to find only one. You have many flowers. So let's try if my idea is good. I'm binarizing the saliency map, and I'm segmenting out the most salient region. And you see, actually, we get many regions altogether. So using this as a first step, I just assign an arbitrary time of permanence in the most salient region, a transition time, and I build an animation. I just load this. The code I'm using is in the notebook, but it takes time to generate and raster the 3D things. And so I just call back this animations list of GIF, and then you have the gaze that is moving through the salient region, and this would simulate, hopefully, the correct eye movement. Of course, this is really crude, but I didn't want to load too much code in this presentation. Another application is that is basically built upon the GrowCut segmentation I showed you before, is done with a new function that you have. It's called remove background. Remove background uses like not just GrowCut, many segmentation methods, and it knows a bit more, and it has an interface you can use to specify things you want to be done. So for example, let's get back the cat. So would we like to segment this without the markers? And if I just call remove background, it will understand where the background and foreground are, because this has a uniform background that is extending till the edge, is all connected. So it really is, you don't want to lose time creating the marker for something this easy, and remove background will do that for you. But what if you have like a different kind of image? This one here, this is a green screen. So this is why the name of the section. So you see here that if I call remove background, it will remove the uniform green background, but not between the legs of a jaguar, because this region is not connected. So it cannot possibly understand that is part of the background. So in this case is where the interface kicks in. So I use dominant colors to get the main colors in the image, and I get the closest color to green in the image. And then I call again remove background, just specifying the background color. And in this case, you have much better removal. So, and then I can, of course, like choose another image as a background, a bit of pre-processing, and I put those together. And you can do this not just with images, but also with videos. Do you have time for this? Yeah, I think so. So let's here we have a poor guy from Wolfram that was working at PC, and we filmed him in, I think it was in Champagne, not really the best place in the world, and this guy is working in front of a green screen. So let's say we want to remove this green screen and put this guy in a better place. We do the same thing we've done before. And in this case, we want a bit more control because images are varying. It's not a clean green as it was in the image. So we use a second parameter which specifies the color distance, the maximum color distance that we want to allow in this processing step. So we do a first passage of removing green, and we see what we got. So we remove most of the green, but you see here behind, just below the arm, you have a darker shade of green. So I just use the pixel tool to select that green, and I put that color here, and I'm doing a new passage of remove background using a different color with more control distance, because this is really dark. I don't want to remove all the black from the image. So now you see I've removed all the remaining green part. I will do a bit of erosion to take out the boundary and a blur to have a better result. We import a better workspace for this poor guy, and when we place this poor guy in a better place. So Another application that you may have seen today, a demo of a new couple predict classify. That is really cool, it's really neat. Unfortunately, is just they just started to implement that for images, but I wanted to stress it a bit and see how it will work natively without doing much stuff. Just let's feed images on that. So I took this EL face database, which is like I think 15 people in 11 different expressions, and I say, okay, let's try to see if with predict and classify I can just pick random sample of faces for each person. These are just the original images. So let's take a random sample. Let's build with an association a training set, and I'll just call classify with a training set. Just this. I just want to see how good it is without anything else. So this will take, oh, okay, it's done. So let's see. You can call some information now of the classifier. So let's see what it has done. It has conformed the images, taken the image pixels, standardized them, reduced the dimension with I think, principal component analysis, and prepend one. I don't know why it's done because I've not written this. But if you look, for example, the matrix plus, this is the internal representation of the image. This is like the result of a principal component analysis. Then we ask, what are you doing this? Okay, this classify using logistic regression. Unfortunately, this is really big. It has a lot of numbers because the images, even if they are small, is like will have in total like some millions of points in the end of the data set. So I just show this is an example of a function that is using with the logistic regression. So it's basically explanation cutoff. And you will have this for every feature in the data set. And it will try to place the images on the right side. So let's test the classifier on the training set. And actually we see that it has correctly recognized all of the data set. Let's see the faces, these guys. So, okay, first step done. Now let's use the remaining part of the data set to see how good it will perform on that one. So let's get the accuracy. Is actually pretty good. Just for feeding the images, we get 90% rate of recognition. Let's see what the problem is. So let's get an idea of the results. So we see here the faces in green are correctly recognized. The faces in red are not. And we see that mainly the problem is uneven illumination, because in the set I have different expressions and also different light condition. You have light from the left, from the right. So this background is really messing up a bit. So let's do a really minimal pre-processing to see how this can be like partially solved with like few lines of code. We just take out the faces using the same thing that Marcus did with his face this morning. We use like find faces. We trim it, and then we equalize all the images with an histogram transform, just to try to get rid of this uneven illumination. So this will take a bit more. Okay, done. So this is basically the final result. We have like smaller images, just a face. Let's train a new classifier with this. And let's do basically the same measurement that we were doing before. So, okay, perfect recall rate on the training set. Let's go on the test set. Okay, we gained 6% just with this simple pre-processing. I think this is really neat because this function, it hasn't been yet optimized to work with the images. So you can do, of course, you can convert your images in data. If you have a specific pipeline in mind, you can do that yourself. We are working to make this automated a bit, but I think it's already neat that like it get this recall rate. And then if we check the images, we see that basically these two errors were here before, and we have still one that is a bit uneven. It wasn't able to get. Of course, if we do more pre-processing, we can try to equalize even more the illumination, and this probably will solve this problem. But this is a bit beside the point. Thing is, I see really potential for this function, and you can link up whatever kind of pre-processing, post-processing you want, and just feed it predict classify, and you will have basically your basic machine learning in Mathematica. So, what are my final remarks? Marcus, what have you done to my computer? Okay, I had some final remarks. I will just tell you about that. So basically, this whole computer vision, machine vision field it's really big, it's huge, and is really blowing up. A lot of people are working on that. And we, with Mathematica, we are really striving to provide either building blocks or higher level algorithms to like keep on par on this kind of applications. And of course, I've showed just a subset of what is in computer vision in Mathematica, mainly to demo new functionalities. But you have all the old stuff that should have been listed here. So segmentation, image registration. In Mathematica 10, for example, we have extended image line to work in 3D, so you can do 3D image registration now. Image transformation. What do we have, Marcus? And all the old filters are still there, and we are constantly working to improve them. So, thank you. This is it.